call persistence, or what you might call durability, or you might even just call plain old input-output, though we've really been focusing on disks and RAIDs and things like that. What we focus on so far are disks and RAIDs, and really that's it. Those are pretty simple devices. They're what we call a block-based device, which means basically the interface is you can read or write a block. Now, if we weren't that creative, or we didn't really like users or developers, what we would say is, if you want to record persistent information, just use the block-based device. Open up the device, write your important information to block 0, then block 1, then block 2. Turns out that's not very convenient. So what people realized pretty early on is there needed to be a piece of software in the OS, so some OS software, that manages these persistent devices and makes them easier to use, it makes them more reliable, we'll see how that is, makes them have high performance, and all the typical kinds of things that we'd think of when we think about what operating systems do, right? It's a shared resource, and so we have to manage that resource. Remember, the OS, sometimes people think of it as a resource manager. In this case, the resource, we'll think of it abstractly as a disk, though it could be a RAID or a flash-based SSD. The OS is going to get in charge and manage that. And of course, one other feature we might have is protection. Okay, so that piece of software in the OS is generally called a file system. The file system is pretty cool, and what we're going to talk about today is really we're going to start with the API. We're going to start off with what does the file system look like to users. Once we answered that, what we're going to do next is get into the really interesting pieces of file systems work, which is implementation. But we're not going to do that today. We're going to have to understand the API before we can get into any of these interesting implementation details. Okay, so let's start talking about some of our basic abstractions. That's what we're going to talk about first, and then we'll do some real examples using, of course, C and the shell and things like that to understand basically what's going on. There are just a couple basic abstractions we have to understand. The first is a file. We might call this a regular file in contrast to some other files we'll see today. You can think of it as an array of bytes. It has a size, which can grow, of course, or shrink. And in general, the types of files we're going to talk about here are persistent. It's long-lived. So we're going to be interested in, for example, this file I created right here. You can see in Emacs it's telling me, oh, you just wrote out /scratch Ramsey lecture-file systems notes-11-03-13. It's actually a way to specify how to access this file. But in general, I expect this file to be there even if the machine goes down and comes back up. That's what persistent storage devices do. So that's a basic abstraction, a file. Now, we could just have, and I guess I should say one more thing about it. It has some kind of name, has a name, though really files tend to have what we would call a low-level name, which you might think of as a number. And as we'll see, we'll often refer to its file by its file number. Is a common way to refer to a file, though not by users. Users are going to want something more user-friendly. So that's a file, an array of bytes. We can read or write any part of it as we want. We can grow it, we can shrink it. But we're going to organize files. We're going to start to build a little bit of structure on top of this by providing what we call directories. A directory is actually just a special type of file, and it happens to, you can think of it as an array of records. And each record maps some sort of human readable name to a low-level file name, which, as we said before, is a number. So you can think of a directory, for example, might say, oh, there's a file, you call it foo, but actually I think of it as file number 1000. You call this one bar, actually I think of that as file 1001, and so forth and so on. And just like files which you can create and access, you can mess with directories, but it's a little bit more limited, and we'll talk about some of the interfaces that you deal with when dealing with directories as well. Now all of this leads to what you might call the file system hierarchy, or what you might call a file system tree. That tree in Unix-based systems allows us to refer to any file by its name and then be able to access it. It's a tree. It starts at what we call the root directory. The root is just called / /, and of course all the slashes we use in the Unix world are forward slashes. Backward slashes are for terrible systems. And it allows us then to refer to a file by nesting. You can think of a directory as an array of records, and it maps human readable names to low-level file names. But you can make sure you understand this. A directory can contain files or other directories, which we might call subdirectories. So our root directory usually have some stuff in it, like it might have more directories in the root, and they might have directories in them, and each might have files as well, etc. So if I quickly pop out of this and I do an ls on my own machine of the root directory, you can see there's a whole bunch of stuff up there. Most of them are at the very highest level, are directories. And then if we do an ls of /scratch, you can see, oh, there's some stuff in there, /scratch remz, there's some stuff in there, /remz lecture file systems, there's a bunch of stuff in there. So we can refer then to a file by this full path name, which is called an absolute path because it starts at the root. It says the root, in there is a directory called scratch. In that scratch directory is a directory called remz. In that directory there's something called lecture file systems. And in there's a file called notes for today. And we can even cat that file and see exactly what we've written so far. You can refer to that file by what's called its full path name. Okay, so that's a file system tree, and we'll talk a little bit more about how we assemble such a tree, because it turns out you can actually paste that all together, not from just one disk device, but from many devices. You can bring together subparts of that tree and put them all together in one big unified tree, and that's what Unix systems do. Okay, what are we going to look at now? We're going to start looking at some file operations. How do we, for example, do things like create and access files? So let's start with file creation. To do that, we'll look at a particular piece of code called create.c. In fact, to create a file, we can either call open, which we'll talk about in a moment, or call actually the direct create system call. Ken Thompson famously, when asked about, hey, what would you have done, looking back on Unix, which is a huge success, what would you have done differently? And he said, very curtly, I would have added an E to create. So that was the only thing that he viewed as was wrong with it, which is kind of humorous and perhaps a bit obnoxious, but it is kind of irritating. There's a bit of a mindset back then, before the era of modern editors, which do a lot of completion for you, and save you keystrokes, that you should really make everything the minimal number of letters. And so you can see that in the history of a lot of Unix. For example, commands like rm, ls, cd, all those two-letter commands, and even the APIs themselves, like create, are a little bit minimalistic. You can do, to understand create or create better, you can look at its man page, and of course you can see right here what it takes. It takes a path name, which is, hey, what file do you want to create? And it takes a mode. The mode says something about, we can look at it down here. basically it says something about permissions, like who should be able to access this file. And this says, I want to be able to read, write, and execute it. And you can look in the man page for more details. Open, by the way, also commonly lets you create a file. You just pass another flag. There's an extra middle flag of what you want to do when you're opening a file, and o_create lets you basically open a file, and if it doesn't exist, create it. So that's simple. To create a file turns out to be a simple thing. Let's go ahead and ls file1. We can see it exists, so I'm going to remove it. So now we're going to compile that create program. Hopefully it compiles. It does. We're going to run it. And then you can see when we're done, that file exists. If we cat it, well, it's empty. That's not too surprising. It's a zero-sized file. Oops. And that's because we just created it. We've given it a name. We've created it. We've made some structures in the file system to remember it, but we haven't put anything in it yet. So that's not too exciting yet. Now I want to do one more thing. I want to show you a very useful tool called strace on Linux. On Mac it would be called dtruss. Every system has something like this. On old systems it used to be called truss, but on Linux it's strace, which is probably the system you'll deal with it if you deal with it, or on a Mac, I suppose. And what this strace does is it allows you to, it's basically a system call tracer. So what you do to trace the system calls of something is you basically just say, I want to run whatever program with whatever arguments, and I just put strace in front of it. And strace, doing some very cool stuff, instruments the system so as to produce a system call trace. So we run that, and we can see actually a bunch of, starting with an exec call to run create. You can think of that as the first system call that exists for this process. You can see what happens. A bunch of stuff happens actually to set up the address space, so we're going to ignore almost all of that. And when the program finally runs, you can see the create system call occurs here, and in fact you can see exactly what it returned as well. It returns a file descriptor, and that's all we've done here. So we've created and we've passed in a flag to specify the permissions. So that's pretty cool, and we're going to use that to understand better what different programs are doing, and you should always use that. Anytime you don't know what a command line program is actually doing, what system calls it's making, use strace or dtruss and figure it out. And then you can know a lot more about what a program is actually up to. Okay, so that's file 1. We've created it, but now what we're going to do is we're going to actually access a file, which means we're going to open it and perhaps read it. These are system calls you might be familiar with. Again, very low-level abilities to open and read files. We're not going to write a program to that. We're just going to use cat. Somebody's already written this program for us. You can see cat of file 1, not too interesting because there's nothing in there. We could, of course, though, do an strace, and then what we'll see is something more interesting. We'll see that cat opens the file. It does an fstat on it probably to get its size, and then does a read. Now that read returns 0 because there's 0 bytes in the file, so there's nothing much to print, so cat just looks like it did nothing. Lazy cat, which is actually quite apropos. So let's put a little bit more stuff in that file in order to make some sense of it, and then we'll go ahead and cat it again, but this time see a little bit more interesting activity. So what are we going to do here? Let's say we echo something into the file. Echo is just does this, just prints out whatever you have there, and if you redirect it into what we called file 1, we can then go ahead and see that there's something in there. Great. In fact, we can see the size of file 1. It's actually 2 bytes. You can think of it as an A and a \n. And then if we do an strace, then we'll see a little bit more activity. We'll see an open of that file, again the fstat, maybe to check its size. We see a read, which returns 2 bytes. And then you see a write, which is kind of cool. That write is to file descriptor 1 as a Unix pro, or a burgeoning Unix pro. You should be understanding at this point that that means I'm writing to standard out, which you can think of as printing. And you can see it's writing exactly those things that it just read. In fact, it gets back 2 from write, says, oh yeah, you read 2 bytes, then you wrote them. Then we try to read again. We get back nothing, and we're done. Pretty nice. So let's do one more thing. Let's make a little bit bigger of a file. Let's say we make it 5,000 bytes or something like that, or 5,000 2-byte things. We can use echo again. Now I'm going to put two redirections like that, because in the shell I'm using, which is TCSH, that means don't just overwrite the file every time you're doing, but append to the end of the file. We'll talk about how to do that programmatically, but that's how you would do it in the shell. And we'll just say that, and then we'll end. And you can see, again, if we look at the size of the file, that it's 10,002 bytes, because 5,000 times, and the first time, we wrote 2 bytes to it. And now if we strace, we can see a little bit more interesting activity. Now I'm going to have to pipe this into less in order to really understand it. But you can see what's happening here. We open the file, then we do a read. Actually, read now asks for a nice file system kind of block size amount, 4K. Gets back 4K, and then writes out the 4K. And of course, we can go ahead and skip ahead to the next read. You can see we call read again on that same file descriptor we get back from open, and then we get back 4K again. We look for the next read. This time we ask for 4K, up to 4K, but we only get back 1,810 bytes. We write those out, and then we just pretty soon get to we're all done when we try that last read. So let me explain one little piece of what's going on here. When we open a file, what we get back is something called a file descriptor. We've talked about this a little bit before, but this is just an integer, and it's going to be used as what we might call a handle to read or write or do other things to files. So our general kind of protocol for file access would be open to get a file descriptor, and then when we do reads or writes subsequently, we pass that file descriptor and maybe a buffer and a size, a pointer to a buffer where the data will go and how, the kind of max size that buffer can take, and that's how we read from a file. What read returns is the number of bytes read, but it does something else too. It internally, what we're going to do is we're going to track, when we open a file, we're going to make an entry in what we might call an open file table. You can think of this as a per process thing. Each process has some list of open files. And what each entry is going to track is something simple. It's going to track a file offset. In other words, when we're reading or writing this file, where in the file are we right now? What read does then, when you say, hey, I want to read from this file descriptor, and I read so many bytes, what it does is it internally updates the file offset to whatever the current location was when you began the read to the current plus bytes read. So let's say I open a file. The offset at that point will be 0 because I want to start reading the file. Then I call read, and let's say read reads 10 bytes for whatever reason. Then the offset will be set to 10. And when I, for example, if I call read again, let's say I read 20 bytes this time for whatever reason, the offset will have been, what part of the file I'll be reading is, this means I'll be reading bytes 10 through 29. I'll be reading, starting at 10 and reading the next 20 bytes, and the offset at the end of that will be 30, assuming it's successful. So this one, of course, then is reading bytes 0 through 9. So this is a really simple streaming kind of interface where when you open a file and you just repeatedly call read on it without worrying about it, you know you're going to get the next so many bytes of the file. You don't consistently read the same bytes. There is a slightly different interface you can use, which we'll talk about perhaps, called preread, where you actually specify the offset as well. You can see this by doing a man on that. You can see I specify the file descriptor, the buffer, the size, and an offset at the end. And if I do that, then basically, this ignores ignores the current file offset when reading, when choosing where to read from, though it may update it. So anyway, that's reading from a file. In a second, we'll learn about how to do things a little bit more interesting, like writing, deleting, and so forth.